Capacitors are one of the most fundamental electronic components we use. You would have to look very hard to find a circuit which didn't have a capacitor in it. But do you really know about capacitors? Stay tuned till the end, as this video covers all the fundamental aspects of capacitors. The capacitor symbol has two parallel lines, either flat or curved, representing how the capacitor is made. A curved line indicates it's polarized, likely an electrolytic capacitor. If the symbol lacks polarity indication, it's likely a non-polar capacitor. Let's explore the internal components of a capacitor. By delicately removing the outer plastic label and metal cover, we can reveal multiple layers of rolled paper inside. These layers can be carefully unrolled and separated. This rolled paper comprises two or more parallel conductive metal plates, each of which is connected to a terminal wire. These wires serve as the connection points to the rest of the circuit. Importantly, these parallel metal plates do not physically touch each other. Instead, they are electrically isolated by high-quality insulating material layers commonly referred to as the dielectric. The symbol representing a capacitor precisely illustrates this arrangement. Two parallel lines within the symbol represent the conductive plates, and the space between them signifies that the plates are separated by a dielectric layer. Using the water analogy, we can understand the behavior of capacitors more easily. Imagine two pistons, each containing water, connected by a pipe. When we apply a constant force to piston A, water starts flowing to piston B due to increased water pressure. This phenomenon is akin to the flow of electric current in a circuit. When a battery is connected to a circuit, electrons move from the negative terminal to the positive terminal. However, in the context of electricity, we consider current to move from the positive terminal, high potential, to the negative terminal, low potential. Here, we have an elastic chamber connected to a water pipe, acting as a barrier between two sides. Water from side A cannot flow to side B, and vice versa. We've dyed the water in side B with green color, but it can't mix with the water in side A due to the membrane's impermeability. This elastic membrane can stretch to a certain degree, allowing the piston to move based on the water pressure difference between the two sides. The membrane halts its expansion when the elastic force matches the applied force. Now that we've stored some energy in the membrane, if we disconnect the pistons and connect the two ends of the chamber, the membrane can move the water in the opposite direction and return to its initial state on its own. Initially, we store energy in the device, and then we can use the stored energy to do useful work. We can plot the membrane resistance force over time. Now let's examine the process in slow motion. Initially, the resistance force is 0. When we apply an external force, the resistance force doesn't increase instantly. It begins from 0 and then rises rapidly. However, as the membrane starts to expand, the rate of increase of the elastic force decreases over time until it matches the applied force. Now let's remove the pistons and connect the two ends. The force begins to decrease rapidly. However, as the membrane starts to contract, the rate of decrease of the elastic force slows down over time until it becomes 0. Can you predict what occurs with the water flow during this period? Initially, the membrane is in its resting state, almost as if there is no membrane present at all. Consequently, even a slight force can move a significant amount of water through the pipe. However, as the water begins to move, the membrane expands and starts to exhibit resistance to the water flow, causing it to gradually decelerate. This process continues until the water flow eventually comes to a halt. If we remove the pistons and connect the two ends of the chamber, the membrane can move the water in the opposite direction and return to its initial state. Initially, a significant amount of water flows in the opposite direction. However, as the membrane begins to contract, the force decreases, causing the water flow to gradually decelerate. Let's compare these two situations. Understanding this water analogy will help you better understand how capacitors work. The negative water flow indicates the water is flowing in the opposite direction. It's important to note that when we add water to one side, the same amount of water leaves from the other side. This is how a capacitor works. When we connect a capacitor to a battery, here's what happens. At first, the capacitor voltage is 0. Over time, the voltage gradually increases until it matches the supply voltage. If we disconnect the battery and connect the two ends of the capacitor through a resistor, the capacitor voltage starts to decrease quickly until it becomes 0. Now let's consider the current. In the beginning, the current is high. However, as time progresses, it diminishes and eventually reaches 0. If we disconnect the battery and connect the two ends of the capacitor through a resistor, a significant current starts flowing in the opposite direction. Over time, this current diminishes and becomes 0. Here, voltage behaves similarly to the membrane force, as seen in the earlier example. Similarly, current behaves like the water flow in the analogy. Let's explore this further. Imagine a battery with positive and negative sides. The negative side holds a surplus of electrons, leading to high electron pressure. In contrast, the positive side lacks the same number of electrons, creating a lower electron pressure compared to the negative side. This difference in electron pressure is known as the potential difference, measured in volts. Let's turn our attention to the capacitor. It consists of two metal plates separated by an insulating layer that prevents electron flow. Initially, both plates have an equal number of positive and negative charges, resulting in a neutral state with 0 total charge. Therefore, the electron pressure on the plates can be seen as 0. Let's connect the capacitor to a battery. Focus on the right side of the circuit. Electrons from the negative side see that the capacitor's plate A has less electron pressure compared to the negative side of the battery. Thus, they try to move towards plate A. Similarly, on the left side, electrons in plate B of the capacitor move towards the positive side of the battery, attracted by the lower electron pressure. Remember, the electrons can't cross the insulating layer, so as one plate gains an electron, the other releases one. This creates the effect of a continuous electron flow, resembling a current through the circuit. Let's examine the changes in electron pressure. I'll represent the electron pressure of each end using scales. Initially, there's a significant difference in electron pressure between the battery and the connected plates. This prompts electrons to move towards regions with lower pressure. Consequently, the electron pressure increases on one plate and decreases on the other. As the electron pressure difference diminishes, the electron speed slows down, causing a decrease in current. Eventually, when the voltage across the battery and the capacitor becomes equal, the current stops entirely. This clarifies why the voltage difference between the two plates begins at 0 and gradually increases. It also explains why the current decreases over time and eventually reaches 0. It's important to note that as electrons move, the battery's voltage undergoes a slight change, but this alteration is minimal and can be disregarded compared to the capacitor's voltage change. Now let's remove the battery and connect the two ends of the capacitor through a resistor. Initially, there is a significant electron pressure in plate B and a very low electron pressure in plate A. Consequently, electrons rush towards plate A through the resistor, resulting in a high current but in the opposite direction. Over time, the electron pressure difference decreases, causing the electrons to slow down gradually. When the pressure difference reaches 0, the current stops. Now that we have a basic understanding of capacitors, we can explore their behavior further. When we store energy in a capacitor, it is known as capacitor charging. Conversely, when we use the stored energy, It is termed as capacitor discharging. Let's continue our exploration. We've modified our circuit to observe capacitor charging and discharging. Initially, both plates are charge neutral, resulting in zero capacitor voltage. If we turn on switch S1, current will flow, and the capacitor will start to charge. Let's consider what happens in detail. When one electron moves to plate A, its charge becomes -1. And another electron leaving plate B brings its total charge to +1. This slight difference in charge causes an increase in the capacitor's voltage. Continuing this process alters the total charge on both plates, consequently increasing the capacitor's voltage. The coulomb is the unit of electric charge in the International System of Units. 1 coulomb is equal to approximately 6 quintillion positive or negative charges. The capacitance of a capacitor is the amount of charge, measured in coulombs, needed to change the voltage across the capacitor by 1 volt. Capacitance is measured in units called farads. Let's assume this capacitor needs Q coulombs of charge for each plate to change its voltage by V volts. We can find the capacitance of this capacitor by dividing Q by V. The capacitance of a capacitor is typically labeled on the component, along with the voltage rating and other details. For instance, a capacitor might be marked as 100 volts and 470 microfarads. This means the capacitor has a capacitance of 470 microfarads. In simple terms, it requires 470 microcoulombs of charge to change its voltage by 1 volt. The voltage rating indicates the maximum voltage the capacitor can handle without getting damaged. In this case, the capacitor can withstand up to 100 volts. Some tiny ceramic capacitors have 2 to 3 digits code printed on them. The first 2 numbers describe the value of the capacitor, and the third number is the number of zeros in the multiplier. When the first 2 numbers are multiplied with the multiplier, the resulting value is the value of the capacitor in picofarads. If there are only 2 numbers, it means there is no multiplier. You can read the value of the first 2 numbers in picofarads. Let's revisit the construction of the capacitor. It consists of 2 metal plates separated by an insulating material layer. The capacitor's capacitance, indicating the charge it needs to change its voltage by 1 volt, depends on 3 main factors: the surface area of the conductors, the distance between the conductors, and the unique permittivity of the insulating material, which depends on the material. We can calculate the capacitance using the equation. Capacitance increases with the surface area of the conductors and the permittivity of the insulating material, while it decreases with the distance between the conductors. We have a circuit like this. Let's assume this capacitor needs Q1 amount of charge to reach the battery voltage Vs. As we discussed earlier, the capacitance of the circuit is given by the formula C1 equal to Q1 divided by Vs. Now we need to add another capacitor to this circuit. How can we do that? We have 2 options: parallel or series connection. The total capacitance of the capacitors changes depending on the selected connection method. Let's consider the parallel arrangement. Imagine both capacitors are connected to separate batteries like this. Suppose to increase the voltage up to the battery voltage, C1 needs Q1 amount of charge, and C2 needs Q2 amount of charge. We can express Q1 and Q2 using the voltage and capacitance of each capacitor. Let's rearrange these equations to make Q the subject. Now, instead of 2 batteries, if we connect both capacitors to 1 battery like this, C1 still needs Q1, and C2 needs Q2 to reach the supply voltage level. To determine the total capacitance of this circuit, consider a single equivalent capacitor that replicates the combined effect of C1 and C2. This equivalent capacitor will have a capacitance value that represents the total capacitance of the circuit. This capacitor C3 needs Q1 plus Q2 amount of charge to reach the supply voltage, so we can write the capacitance of C3 as Q1 plus Q2 divided by Vs. Here we can replace the Q1 and Q2 from the C1, C2, and Vs. We can simplify this expression by canceling common factors, resulting in a relationship like this. In conclusion, when capacitors are connected in parallel, the total capacitance of the system is just the sum of the capacitance of each individual capacitor. In a series capacitive circuit, the same displacement current flows through each part of the circuit. Let's examine this more closely. For clarity, let's name the plates as P, Q, R, and S. If one electron moves from the negative side to plate P of C1, one electron has to leave plate Q to plate R of C2. This process continues, where to accumulate one electron on plate R, plate S has to release one of its electrons. These electron movements occur simultaneously. Hence, each plate always holds the same amount of charge, and the applied voltage divides across the individual capacitors. Now we can proceed to calculate the capacitance of each of these capacitors. Let's rearrange these equations to isolate voltage as the subject. According to Kirchhoff's voltage law, the sum of the capacitor voltages must equal the source voltage. By replacing V1 and V2 with the capacitance of each capacitor and the charge amount, we can express the equations accordingly. To determine the total capacitance of this circuit, let's consider a single equivalent capacitor that replicates the combined effect of C1 and C2. This equivalent capacitor will have a capacitance value that represents the total capacitance of the circuit. Capacitor C3 will reach the supply voltage by utilizing the Q amount of charge. Hence, we can represent the capacitance of C3 as Q divide by Vs. We can replace Vs with the charge amount and the capacitance of each capacitor. Simplifying this expression by canceling common factors results in a relationship like this. In conclusion, the reciprocal of the total capacitance of capacitors connected in series is the sum of the reciprocals of each individual capacitance. That's all for today's video. I hope you found it helpful.